Hello, everybody. Thank you for joining today's webinar that will be exploring load stability, defining representative laboratory test methodologies. This is, of course, the second webinar in the series, and a recording of the first is available for you on our PPT group events page, and I will put a link to that into the chat box a little bit later. Again, for those of you who've been with us before, you'll know that this obviously is a Lansmont Corporation webinar. Lansmont falls under the umbrella of the Physical Properties Testers Group, or PPT for short. And the PPT group consists of various expert brands specializing in physical properties testing solutions, encompassing areas like tensile and compressive strength, torque testing, textile analysis, and real-world dynamics such as shock and vibration. The other companies within the PPT family are McMesson, James Hill, and Telluris. And again, once you go onto the PPT group page, you can see more about those brands if you're interested. And if you want to know more about the individual brands, it would all be visible on the PPT group site. Most of you will know our webinar host for today, Eric Jonassen, Lansmont VP of Technology. And today we again welcome a special co-presenter, Dr. Laszlo Horvat, Associate Professor at Virginia Tech and Director at the Center for Packaging and Unit Load Design. And my name is Sharon Smarenberg, and I'm one of the organizers. As always, we'd like to keep it as interactive as possible, so do feel free to ask questions. You can use the question box throughout the webinar to type in any questions you may have. We will then address these questions at the end of the webinar. The webinar will be recorded, and you will receive the recording at the email you used for registration within roughly, we try to do it within 2 days of the webinar having taken place. So please feel free to share the recording with anyone who you think might find it of interest. And with that, I'll turn it over to Eric.
Thank you, Sharon. And I'm turning my camera on here real quick. And maybe, Sharon, if you can give me a thumbs up if I'm...
Yes, we can see you, Eric.
Okay, I'm sorry, because I can't see it with my control panels. I'm sorry, everybody, but make sure that I'm visible for the moment anyway. Introduce myself, say hello, good morning. I'm actually in California at our Monterey, California headquarters, just so happens today. So this, for myself, that means over the last year, I've presented from the East Coast of the United States at once upon a time, and way over in New York, and I'm based in Michigan and now in California. So nobody needed to know all that, but I guess I've covered my grounds on showing that I can hopefully deliver webinars wherever I am or wherever I need to be in the United States. So I am at our corporate headquarters right now, and a little bit out of my comfort zone in how I deliver these things, but it's all working. Looks like it's going to work well, and I'm happy to be here. I'm going to go through this. I'm going to do most of the presenting today, just because make sure that it goes smoothly. Laszlo is with us. He's going to join at the end. I'm going to touch on some things that we're doing together with Laszlo and Virginia Tech, as well as some other universities, but specifically with Laszlo at Virginia Tech, and then he can join at that point to answer any questions as related to what kind of research that might be taking place, and some of even the short courses that we're going to cooperate with that deal with these kind of subject matters, not just this, but this topic of load stability. So I'm going to save it. I'm going to do all the talking for now. I'm going to go ahead and turn off my camera. Thanks for joining me and us at this point, and we'll talk to you on the other side, or see you on the other side when we get done here. So yes, here we go. We're going to talk about load stability yet again. So the first time we talked, that I presented a couple weeks ago, we talked about more of the measurement side of it, kind of the field dynamic. In this whole field of the lab, the Lansmont approach, measure what happens in the environment, use that measurement to drive the testing. We kind of addressed the unique characteristics associated with load stability dynamics in the real world, at a simple level, but we did discuss that. And now what I'm going to focus on today is more of the testing methodologies used over time, not just current. This is not necessarily a sales pitch trying to push any type of equipment or technology. It's really more to cover almost all the different means that most of us in our testing community, our packaged product, cargo shipment simulation testing community, what we use to address this one way or the other. Sometimes you might not even realize that that was the intent of the test procedure, or that that's what you're able to evaluate by doing that testing. But I'm going to cover all those, from the maybe from the more simple to the more sophisticated, that are just starting to kind of show their value and capabilities here. So excuse me. So moving forward, why are we talking about this? I mentioned this kind of last time. I mentioned it quite often in presentations. There are pressures, right, to reduce the use of packaging materials. Basically, think of like sustainable packaging initiatives, although it doesn't necessarily even have to be related to sustainability. There's always been pressure. Even for my whole career, I've been working for Landsmart for 35 years. From the get-go, sustainability is almost built into packaging, right? Because no one wants to spend money on something, from a corporate perspective, especially when it's potentially expendable, right? It's a cost. Yeah, it's got a function, but it's a cost. And so there's always pressures to reduce the use of materials one way or the other. Cheaper materials, less materials, and that's kind of the big thing when we talk about load stability, that where it really has an impact, where you've gone from left to right, from something that might be rigid structural packaging to starting to take away that material to the point where it has a negative impact, right? So things become, they don't have that structural integrity, and so things can start becoming damaged or challenged in ways that they weren't intended to be put in those situations, and maybe don't have the performance to survive in those conditions. So we don't want, for instance, this is just kind of showing, a good, you go back there, a good load. We don't want that ending up looking like the load on the bottom where everything is shifted. And in that situation, you have to, imagine that those were pictures of what we call, or what the industry calls maybe curtain cider trucks, which is something that's maybe not used as much, definitely not used as much in North America, much more common in Europe. And when you don't have, rigid structures on vehicles like that, there can be issues, not only just with loads getting damaged in the back of transport vehicles, maybe tipping over, getting damaged, causing logistics issues, but there's also a safety concern. So if those loads do move, tip over, fall outside the footprint of the transport vehicles themselves, they can hurt people. And that's a major risk and no. So it's become a much more prominent issue. Not just, it's been an issue, I'd say, that I've been aware of for like the last 10 years in a focus of conversation at various conferences and that I've attended, around the world, quite frankly, talking about load stability and what to do about it from a testing perspective. So rules and regulatory requirements. In the United States, who addresses this? Who addresses load stability? Like, really specifically calls out those kinds of hazards and quantifies somehow or characterizes those hazards in terms of their severity and amplitude. The only one at this point in time in the United States is the Federal Motor Carrier Safety Administration, FMCSA, and they publish cargo securement rules. In Europe, it's all addressed under a EU roadworthiness directive. So there is standardization and regulation associated with load stability and cargo securement. From the EU side of things, it's a much larger, much more, I would say, advanced and more defined in Europe than it is here in North America right now. And the key organization that some people may know about, may not know about over in Europe that deals with this is called, I pronounce it UMOS, from the English side or the United States, how we pronounce it. Hey, I've heard it called OIMOS. It depends where you are, but it stands for European Safe Logistics Association. And it's an organization that focuses on cargo securement and standards associated with safe logistics. And it's from training to loads inspections to cargo securement practices, but also testing side of things. Put the website on there, but the big thing that as we talk about test methods moving forward, the relevant standard that I'm going to mention here is this UMOS 509, which is a test method for load unit rigidity. And you can see my mouse here. It says UMOS 509 is included into Annex 3 of the EU directive on technical roadside inspection and roadworthiness of commercial vehicles circulating in the Union. So this is an organization that does have a standard. It has a number of standards, but this relevant standard that tells you how you need to test unit loads to prove their roadworthiness. In the U.S., again, they're just touching on the website for the Federal Motor Carrier Safety Administration. A little bit of description of who they are and how their rules apply. If you look at the performance criteria called out within the FMCSA, it talks about these things. Now it says that the loads, that unit loads must be capable, or cargo must be capable of handling 0.8 Gs of deceleration in the forward direction, 0.5 Gs of acceleration in the rearward direction, and half a G or 0.5 Gs in the lateral directions. So this talks about, from the US side, performance capability, but what it says, in the print down here, it says generally motor carriers are not required to conduct testing of cargo securement to determine compliance. So, I don't think many people, at least that I'm familiar with, let's say in the testing community, they might not even know these performance criteria exist from the FMCSA, but because they're not really required either, or there's no testing requirement, how do you go about proving it? It's just a number. What is the test? How do you go about that test? I don't think there's anybody that's acting upon those very, very much that I'm aware of anyway, from the US side of it. So there's some lack of clarity or lack of direction from how do you test and simulate to address things here on the US side of things. But like I mentioned, the implications of load stability are significant. So this is just a couple more images showing, if loads shift, obviously on the right, again, that's pull the curtain up on the side of the truck. You see the loads have all shifted, the whole load, not just one pallet, but everything in one direction. In this case, I guess it's better than shifting to the lateral side or outside, the side of the truck. They're all shifted in the backwards direction. But you see in the top left image, of course, there's something where the load is obviously has come out the side of the vehicle, and that's actually that looks like also a curtain sider truck. Well, if that happens going down the road and there's a bike lane right there and someone's riding a bike, I shouldn't be laughing, but there's serious implications there, right? For maybe damage if it's another vehicle, but obviously safety. It can hurt people, it can kill people, and so that is a really big issue. And one that they address much more strictly or directly, I would say, in Europe as compared to the U.S. So when we talk about load stability, some of the ways that we define, let's say the responses of loads, is it just that they tip or they shift? I mean, how do you describe the responses to those kinds of dynamics? And these are just some examples. What we talk about is, loads can slide on their pallets. If it's a slip sheet, they can, one of the ways that they shift is by sliding. Another is by buckling. Let's say, the bottom layers, depending on what the materials are, if they're weak and susceptible, or they get point loaded because of the rotation, or, everything does shift above the weight CG shifts, now causes the loads to buckle. That's a result of a response to these kind of unique lateral dynamics that occur in transport. This is something called stepping. So it's the layers are all shifting, and they're like almost, you could think of it as lots of little steps involved there. So the load is stepping as it's shifting, and then this is braking. So you think of two, or some type of major sections of the load breaking from the other part of the load. And that could be due to failure of stretch wrap materials or something like that. So it's a shifting or a sliding of the load, but it's only sliding a part of the load, where the other load, they become decoupled from one another. And so again, it's not a shifting or a tilting kind of a scenario where it's unsafe because it's tilting or tipped over, but because it has shifted and it's shifted outside the footprint of the pallet, there's a big risk there. There's a big risk there, and there's a big pain for people that have to handle that from the logistics side of things, loading and unloading that pallet after that may occur from the trucks or transport vehicles. Excuse me. So now what I'm going to do is just talk about some related testing. So different ways we have historically addressed load stability or seen the effects of what these dynamics can cause and what that looks like from a testing perspective. So, inclined impact testing. I'm being quiet while it runs. Sorry, for those that have noise. And let me just say what I often do say when I'm presenting. If the videos don't play, sometimes they play well when I present, sometimes they don't. And what I just promise everybody is that in the recorded session that we produce, I go back in and make sure that I overlay the absolute, original videos at their proper quality. So when we post the on-demand recordings, all these videos will be at their, perfectly fine, full resolution. All that issue goes away. So apologize if it's not super clear during this broadcast, but it will be on the on-demand side of things, hoping that it does work for you. So inclined impact is one way of addressing load stability, and in ISO 10531 they call out what we call a wedge. So you saw that in the previous videos, and this just kind of highlights here this wedge. So normally in an inclined impact, you have a dolly or a carriage that travels on a track, and you retract that dolly certain distances to allow, the farther you go back, the faster the dolly or the sled is going when it hits the backstop. But normally that's done at a 10-degree angle, right? You put a pallet on there, and that pallet and the load is also at that 10-degree angle. Well, if you do that, the intent of the test is not to challenge load stability. It's actually to impart a horizontal shock or impact into the side of the complete load. So, this doesn't show it, but let's say this was rotated back down 10 degrees. Well, instead of there being a gap here, that there would be no gap, and the unit load or pallet load would impact directly against the backstop. So what people have done is, get creative once upon a time and say, all right, what if we build this wedge that brings back the surface of the dolly to level? Instead of at a 10-degree incline or parallel with the rails, let's raise it back up 10 degrees and then let the unit load travel on that wedge as it goes down. And so now the impact of the dolly is really between the dolly or the carriage in that wedge in the bulkhead, but not the unit load. So that allows, upon impact, the loads to move, right? You allow the loads to respond and displace. And that's a legitimate way of looking at unit load stability. The problem is there's kind of a lack of control, certainly with what type of input you're putting into the load, the duration of it, the amplitude of it. Really the only thing that you're able to control is the speed at which the dolly is moving into the bulkhead. One other mode that whether people realize it or not, that you can challenge the stability of a load is with something called mechanical vibration or rotary vibration. And really, we would call it more, like mechanical shaking. So rotary shakers, old technology, right? This is, Landsmont system, just kind of showing the motion, the circular synchronous motion that you would get on a rotary shaker, where it's 1 inch of vertical displacement, but it's moving in a circular motion. And you can do that at fixed frequencies. But what you're able to do, really, if you think about it, in some ways, it's almost like a multi-degree of freedom. It's 2 degrees of freedom that you're putting into the test items at one specific frequency, but you're able to dwell at that frequency. And this might be hard to see. And that's not our vibration system, but it's mechanical shaker. And it's beating the heck out of that. In this case, it's a unit load. It's a product. It's not a pallet load of goods. But you see what that's another way of certainly challenging. In more of like an integrity test than it is certainly simulating anything. But that is a way to really challenge the lateral performance, protective performance of packaging, primary, secondary, tertiary packaging, and evaluate, whether things are going to hold together or not, or deliver the protection that you want. So that's, rotary shakers are good for that. The only concern that I would have from my side of things is it too severe? What does it simulate? How do I correlate that to anything that I might see in the real world? But it's definitely going to challenge things from a stability perspective. Rotational drop testing, as simple as it is. Lots of people, I'm sure, on this that are joining here perform this type of testing, and it absolutely allows you to impart or challenge the ladder stability of loads, right? You're creating a rotational acceleration as soon as you pull or initiate the drop, and that creates the motion that challenges things from a lateral perspective. And so that's just another good way of getting an indication in a hurry. In a simple test, do a rotational drop test on a unit load, you'll know quickly, in my opinion, if you're going to have any issues or not associated with load stability, because you're able to see the response, kind of immediately in an isolated fashion. So rotational drop testing, another way of looking at load stability. Horizontal impact testing, old video, but a good one. Actually a big sled with multiple unit loads. This is the same sled, but looking at more of a load stability type of an impact. And this is different than that type of test system is different than a incline impact system, is where we can specifically program the type of shock pulse that's going into that sled and whatever is the unit loads that are placed on that sled. So in this case, it is programmable, and so it's kind of moving in the direction of a little bit more sophisticated testing input, or a lot more sophisticated testing input, in that you can program the shock impulse that's going into the load. The concerns with it are, or the limitations are that you can only go through certain G levels or certain durations, and you're going to include rebound into the testing. In many cases, there's some amount of rebound, which is then you have to figure out, how do I correlate that with the fact that in the real world, when, let's say, vehicles brake, accelerate, or turn, they don't, right? If something comes, you slam on the brakes, the vehicle comes to a stop, there's no rebound associated with that. So there are good benefits associated with that type of testing, but we're still kind of moving in a looking for, or let's say, can we get closer to more like closer to reality with our simulation? Another way of challenging load stability, forklift handling. This is 3D, which is for LTL is a test procedure for the LTL environment. You're testing loads that are going to go through the LTL environment. And so there is something, in not only in ISTA test procedures, but also within ASTM 4169, depending on the distribution cycle, where you can set up an obstacle course. So that's what I kind of tried to show there, was my little forklift driving across this obstacle course. So imagine this from left to right is a run in a laboratory where you have bumps, like almost like, let's call them like speed bumps, that are placed on the floor or bolted to the floor at different locations, predefined locations, different lengths, different heights of the bumps, and you drive a forklift with a unit load over it. Find someone willing to drive your forklift and take the bumps and the abuse as they drive, and this is kind of what that looks like. There's an obstacle course, someone driving over, and no doubt about it, the responses that you're going to see with your unit load on the forks. If you're going over, offset bumps left to right, you're going to shake or generate responses from in the lateral direction. It's going to be rotation. There's going to be side to side dynamic going on, and there's going to be pitch. As you're moving across those bumps, the forks will be bouncing up and down, and they'll be pitching, forward and backward, like a teeter-totter. So you definitely generate a fair amount of motion there. And it's, once again, an integrity test. It's an abusive test, not only on the load, but the equipment, the forklift, maybe the people driving it. And it's hard to control it, right? It's hard to control that, because can you really control, how well can you control the speed of your forklift when you're driving over it? And are you sure that you're hitting the bumps, the same way every time? And then how do you evaluate the test results, once you've driven over your course? But it's definitely, called out and used quite frequently in test procedures. And it is, you can think, some people might think of it as a vibration test or a shock test, but really it's, in my opinion, primary thing that you get out of that is getting an idea of how your loads are going to perform from a stability perspective. Vertical vibration testing. This is another mode. There's actually a test procedure here within ASTM. Might be hard to read, but what this says is ASTM D5415 is a standard test method for evaluating load containment performance of stretch wrap films by vibration testing. Over here, it talks about the actual test procedure, and the procedure starts here. But if you look here, as simple as this test procedure is, it basically says, put your unit load on there on a table, do a sine sweep to determine the vertical resonance of that unit load. Basically, where does your unit load like to resonate or shake up and down, get that vertical response. And once you identify that, you dwell at that frequency. You dwell at that resonant frequency, and you at 4 different amplitudes. 10 minutes at a half a G at resonance, 10 minutes at 3/4 of a G, 10 minutes at 1 G, 10 minutes at 1 1/4 G at the resonance. And that's basically it. And it's like, if you can pass that test, your load holds together. You document that, right? Kind of a pass-fail criteria. But there is a method for this, right? The people work on this. Somebody once upon a time created this. This is a method that gets reviewed. And I'm not sure that many people realize that this exists. Again, from my side, I would question the use of it, because what you're looking at in this example is vertical resonance of a unit load. But what's important to understand is unit loads have also a lateral resonance, right? So big, tall, let's say you have a big, tall, heavy load, and if I was to shake that load, vertically and find resonance, the resonance of that load might be the vertical resonance, where it starts to bounce up and down on the table, might be, I'm just going to say 10 hertz, maybe 13 hertz. It's a frequency, and that's what it bounces. But if I was to shake that same load laterally, it's lateral resonance, where it likes to resonate side to side because of how it's contained, or the weight. And so basically think of it as a tall vertical beam, especially if it's unitized at some level. The resonance there is likely going to be different. It's going to be much lower. So the lateral resonance might be a couple hertz, or 1 hertz, or 3 hertz, but it's going to be on the lower end of things. And that's, probably has as much to do with stability than does the vertical resonance. So you can beat the crap, if you use this test, you can beat the crap out of your unit load, and you might cause failures to your load that have nothing to do with, the intent, stability. You did it because you over amplified the inputs at resonance to unrealistic levels, and you dwelled at them for unrealistic periods of time. But there is a procedure for this. And then horizontal vibration, standalone. So not only vertical vibration, but we make, Landspot makes, a number of companies make. There's actually a large population of horizontal vibration systems out there that are single degree of freedom, but that just shake in the horizontal direction or lateral direction. And so I'm, quite frankly, I don't know that people really, again, recognize that this, either the standards, there are standards that address this within ASTM, for instance, how you go about using pieces of equipment like this, horizontal vibration, what are the test levels, the inputs, the frequencies, can you do random? If so, how do you explain that? But there is a standard for this, ASTM D5112. And what I would say is this is a big project that I worked on, for instance, even early in my career, one of the first major projects that I helped with the installation and training of equipment. This is at Clorox in Pleasanton, California. Was at Clorox, their lab. And all these machines on the left that you see there are vibration systems, all in a pit. But this one on the end, this one down here, that's a horizontal vibration system that was specifically, in their case, purchased and acquired for doing load stability testing, because at that time, especially that time, that was way before e-commerce, everything they shipped was unitized. And so load stability was a big issue for them. And, and so they bought, and, it was part of their normal corporate testing standards to challenge things from a horizontal perspective, both vertical and horizontal. Those weren't simultaneous, which would be simultaneous multi-degree of freedom testing, but they did perform horizontal vibration. And a lot of that technology exists still in a number of different laboratories today. So I'm surprised that we don't, quite frankly, hear more about just even that type of testing as a pushing the bar forward in terms of what we can do to address horizontal, load stability. And then there's multi-axis vibration, which is something that's being talked more and more about in products that are being offered more and more by people in our community. Not, we've had a history with providing this technology. There's other companies, a competitor of Landspot, SafeLoad, that makes this type of equipment, not this specific one that you see here. This was provided by us, but they make multi-degree of freedom equipment. There's companies in Japan, there's electrodynamic shakers that are multi-degree of freedom capability. And this is another area that's growing to say, all right, lateral vibration motion, vertical vibration motion. Yeah, but I can do those things individually or sequentially, but what about if I do them simultaneously? Is that the right way to be challenging loads from a stability perspective, from a vibration dynamic stability perspective? So that's an area that's growing as well. Then Landspot first got into what I'm going to call, as we move forward, acceleration sleds. We first got into kind of a higher performance acceleration sled with an organization in Germany called Fraunhofer. And this is Fraunhofer has a number of institutes throughout Germany, and they have one in Dortmund, Germany, that focuses on cargo securement, or in supply chain solutions, and part of that's cargo securement. And so they had a very large incline impact test system with a large seismic mass, but they wanted to develop a way to take advantage of that large seismic mass for impacts, but also then have a controlled acceleration, deceleration capability to either fire things into that mass or slam on the brakes basically before it ever got to that mass. And so this was our first foray back in the early 2010s in building an acceleration sled. And it's kind of a unique design, and it was over-designed from, I guess, what I would say traditional load stability testing, but that's because it also had the ability to do big impacts at the end. We could crash that sled into a stationary huge mass with bumpers and elastomers. So it was over-designed, but that was our first foray into that technology, and that was back in, let's say, the early 2010s, maybe in the 2012 timeframe. But challenges kind of associated with everything that I've shared right now is they all kind of provide good evaluation of load stability, right? You look at the results or you look at the testing as it's taking place and you go, yeah, wow, look at that. I definitely see that thing moving side to side, or it's swaying, or I did some type of, put some type of dynamic in there and look at sure enough, the load shifted. But it's really kind of maybe, pass fail assessment at the end of it all. It's like, what do you think? Is it going to work or is it not? Are you concerned or not? Thumbs up, thumbs down, pass, fail. And it's difficult, in each of those cases to kind of quantify anything. It's difficult to quantify and compare performance of any of the materials associated with there. How much did it move? And, how much did something move or give in the primary, secondary, tertiary packaging? And can I quantify it so that if I change anything in any of those materials, I can compare the next iteration against the next iteration, so on and so forth. So it's difficult using any of those tests. They're good kind of abusive integrity tests, but how do I use them from a development or engineering perspective to make decisions on better, doing something better or worse? So I say, in this slide, what about objective metrics associated with unit load response dynamics? So this is basically, especially on the right, I'm going to show you, this is basically not only when I do these types of, let's say, side impact, can I measure somehow things like the displacement associated with the response of the load to that input? I see it move, but how do I quantify how much it moved, or with what kind of frequency response did it move? Almost think of it like from a vibration or the oscillation response. What is the mode of the response when I expose it to that? And that's what the right-hand plot showed there. So at Virginia, this is old material, quite frankly, but I always have liked it because to me it steered me in the direction of there's a way to get more out of doing this testing, and it's an example of they used and probably still use older technology like an incline impact test system. So there's a unit load up on a wedge on an incline impact dolly. See, that dolly is at 10 degrees with the floor incline. So they take that back out with this wedge, and then they're going to do side impacts. But what they have here is they've got string pots. Okay, so this is a string pot that's attached. You can't really see it in this picture. You will in a second, but it's a string pot that's attached to a fixed fixture on the back here of their dolly, and it's attached to the load, so that when they do an impact, you'll see it here. What's really interesting there, I see it very interesting, is you see a huge amount of displacement there, right, with that unit load. Not only that, though, but you see an oscillatory response, right? So it's not just this huge displacement, but it comes back and then it goes oscillates back and forth, and it's got some dampening associated with it because eventually it stops moving. But it's got an oscillation, and that oscillation, if you think about it, that's its natural frequency, right? It's its horizontal natural frequency. Well, can we measure that? Are there ways to measure that? Yeah, there are ways, even by looking at the string pot data that came off of that. That's what you're looking at there. It's different, two different locations, measurements taken at the top and the middle. String pot attached to the top of the load, one to the middle, and now we're looking at displacement over time. We can, from that information, determine what the resonant frequency is. So not only do we know how much it moves, but we know at what frequency. And so, there are things we can do from a packaging design perspective to change that, right? With science, we know to make it stiffer if we want to reduce the amount of displacement, or we want to raise the natural frequency of the load. We have the ability to use our packaging resources to make those changes, to make the load stiffer, more material, stiffer material, more wraps. There's just different ways of going about it. But now we've got some kind of quantifiable performance metrics. So bringing us to acceleration sleds. Again, this is a picture of Landsmont. I'm Landsmont, so I'm showing our sled. And again, there are a number of companies that make these. Not a lot of companies, but there are a few. There's a major competitor again that does this as well, and it's much more. And they're based in Europe, and that's where there's a lot more current acceptance of this and use of this type of technology. But this is what we call our true motion acceleration sled. So this is a sled, and this sled does horizontal acceleration inputs. There's no impact involved. So that's why this looks different than an inclined impact test system, or it looks different than a horizontal impact test system. Because what this does is it travels back and forth on the rails, basically, but it's more of a slam on the brakes. We can control the acceleration and the deceleration of this sled very specifically, with really good control, like you're slamming on the brakes in a vehicle, but not to the point where you're hitting the wall. So there's actually a lot of simplicity in something like this, simplicity and elegance in its design and its performance. But there's no big, it's nice that you don't have a big seismic mass or a big wedge that you have to fill full of bags of sand and so on and so forth. And so this, jumping a little bit here over to some field data. This is me. This is something I probably shared even in my first presentation, but this is showing an event that I recorded in my vehicle. Driving down the road, 35, 40 miles an hour, I slam on the brakes. The red channel from our saver is recording in the direction of travel. So as I'm going down the road, I apply the brakes aggressively, and I see a change of over 0.7 Gs. So that's an aggressive in my vehicle, passenger vehicle, anti-lock brakes. I'm able to achieve, really, I was never able to achieve any greater than that, but about 0.7 Gs. And for a pretty long period of time, from 1, 2, 3, about 3.5 seconds, from the point that I slammed on the brakes to when my vehicle came to a stop. And there are key bits and pieces associated with these. It's not just that I hit 0.72 Gs. That's not the only thing that's important here. There's a number of things, right? Because when you really dissect what that is, this is that same event. Basically, I took it into Excel and flipped it or inverted it over into the other direction. Doesn't really matter which, the positive or negative just means which direction was I going in my, was I slamming on the brakes or was I accelerating? That would, it's the direction of the G's that you're experiencing. So I just inverted it because I think it's easier to look at this way. But if you look at it, there's a dynamic part to putting on the brakes, and it's this change. It's the change in acceleration, the rise in the acceleration, and then there's a static part to it. Once I slam on the brakes, I hold it, right? Now I hold it for some number of seconds, and then I release the brakes, and I go from, there's a change, again, a dynamic part of it. And what we call that dynamic part, here I'm labeling it dynamic, but what it's really called is jerk. It's the jerk rate. Change of acceleration is described as simple of a word as it is, but it's a technical, it's physics, it's jerk. And that's important to understand. So it's important to understand the jerk associated with these dynamics, and it's important to understand the static part. So you think of it, again, I would say I travel a lot. So if I'm on the train's in an airport, you hop on the airport and you're going to go to the rental car lot, and you hold on to the bars, right, in the trains. Why? Well, that immediate, you leave the station, that immediate motion that you feel, you stabilize yourself and you hold on, that's jerk. That's jerk. When you go around a turn or a corner, when you leave the station, and you're holding on again, and it's kind of the constant, I'm being pulled over to the left or pulled over to the right, that's the static part of things. So there are really different kind of components associated with these dynamics. And the jerk is important to understand. It could be a big part of what causes the major response, or what triggers loads to move and to shift. And so we have a way of, kind of defining what is jerk. Well, there's a way of looking, kind of deducing that. Really, it's the change in acceleration over time, right? So in this case, if I just looking at the leading edge of that event that I just showed, my slamming on the brakes event, I could pick anywhere, any 2 points, and basically measure the, especially if it's linear, right? A linear change. I can say from start here of 0.25 seconds to between 2.5 seconds and 2.8 seconds, there was a change in acceleration of I measure that acceleration, and so you just basically say, what's the change of acceleration over that time, and that becomes your jerk rate. So that's what you get out of it, is this jerk rate in G's per second. So on the trailing edge, when I slammed on the brakes aggressively, I had a jerk rate of almost 1.5 G's, 1.5 G per second. And when I let off the brakes, after I basically slowed down to the point where I wanted to let off the brakes, there was another jerk rate and let off the brakes of 1 G per second. And that's important to understand. And again, if you look at even the time of change of acceleration, it's about a third of a second, 300 milliseconds in both of these situations. Primary jerk is 300 milliseconds in duration on the leading edge and 300 milliseconds on the trailing edge. So with acceleration sleds, we're able to basically create what we're able to do, or the way you drive these types of systems. One of the ways you can drive these systems is basically to create those kind of time domain profiles. Let me just look at this as time versus acceleration. This is a profile that we can program into our sleds. This is actually breakpoints that come from the UMOS 40509 test procedure. And if I'm trying to achieve a certain acceleration, let's say a peak acceleration of 0.5 G's, using the UMOS time domain profile, one of the time domain profiles, this is what you would program into a sled. Yeah, and there's me plotting those breakpoints. I'm just plotting the points right there, but that's where I would plot those breakpoints. And if I connect the dots, that's what my time domain profile would look like. So what that basically says is that when I start the test, it's going to go from 0 to 0.5 G's in 50 milliseconds, pretty quick. That determines, again, you would call the slope of that line the jerk rate. Then it's going to dwell at a half a G for 300 milliseconds. And then it's going to have another change of acceleration back to 0 in 50 milliseconds. No change of acceleration for a little while because it's doing constant speed, and then it's going to slow down. So the acceleration is in the opposite direction, because we accelerate in one direction, right, as you fire the sled down the rails, but then of course you have to stop it at the other end. So you put on the brakes, literally, for how these sleds operate. So that's what a profile looks like that you would program into this machine. And you see, again, what that leading edge is, that's the jerk rate, right? So we have a jerk on the front end of it. We have a dwell at a constant acceleration. We have a trailing end jerk. We have another kind of dwell as it's just kind of moving at constant speed, and then we decelerate it more gently, right? So this you can think of as the test, the primary test input, because that's where the big acceleration is. But when we slow it down, we are less aggressive with the slowing it down. So we fire quickly, and then we slow down gently. This is one way of describing it. You could flip-flop this profile entirely so that you fire slowly and then stop aggressively after you. So remember, these are acceleration things. So if I flip this around, I could accelerate at a gentler acceleration level, but I accelerate for a longer period of time. That means in the end, I would be going faster. So once I'm going fast, I would then need to slam on the brakes more aggressively to stop. So it just, you can go about these profiles in either direction, where the test is at either the beginning of the event, the physical testing event, or the test is at the tail end of the event. You're allowed to do it in either direction. And this is what it looks like. So it's hard to maybe imagine, but this is what this profile looks like from a testing perspective. Boom. So the test really is at the front end of that. Here it goes again. The major acceleration is at the beginning of that event. That's in slow motion. We accelerate for 300 milliseconds, then we slowly kind of come to a more gentle deacceleration, come to a stop at the end of the travel. That was a higher G event. That was, I think, 0.8 G input in this example that I'm showing, but that's how it works. It might be again hard to visualize that, but that is running that time domain profile. In addition to doing those kind of that type of UMOS time domain profile, you can program in any kind of different dynamic. So this is a dynamic that looks more vibration-like, right? Think of something going around a roundabout, or maybe going over some type of a little bit of a jerking the steering wheel, no pun intended, but jerking the steering wheel left to right, you would get a motion like you just saw there. Let me go back and repeat that. And you see that in this case, it oscillates back and forth. Not all in one direction, it's an oscillation. And what you notice is I'm able to even though I didn't travel very much, I'm actually able to create a lot of response or a lot of motion with my load. So you're able to program those types of events in there as well, which are more vibration-like. And so quite frankly, that's where we're headed with this, is that this has the ability also to do some type of low frequency horizontal vibration input, which is another unique capability to these things, not just doing the major accelerating and braking types of dynamics, but also the oscillation, so that you can determine lateral resonance per unit loads, lateral resonance, and quantify that, how much displacement at resonance, and then have a way to, once you've quantified it, you can go back and with the next iterations and compare it to see if you're doing things, you've made an improvement or change in another direction. So nobody needs to really focus too much on this, but one of the ways we define the performance of these sleds is like, all right, depending on what my payload is, zero, like no payload, 750 kilogram payload, 1500 kilogram payload, how many G's can I exceed? So this is really talking about a dwell. If I want to do a dwell at a constant acceleration, which is almost really kind of a worst case scenario, if I want to expose something to 1 G constant, how long could I do it? With a 750 pound payload, I could do just over 300 milliseconds. That's what it says I could dwell at 1 G, which is really super aggressive. No, I would say most people would never, ever even approach that. But the sleds can do it. But I would never do it because it's way above and beyond anything that you would ever experience in reality in the supply chain, in cargo transportation. That's my opinion. That's my personal opinion from lots of measurement that I've done. But if I wanted to, test a 1,500 pound payload, and I wanted to expose it to something more realistic, like half a G, well, I could dwell actually upwards of 700 milliseconds, which is a very long period of time. 700 milliseconds while experiencing that 0.5 Gs, holding that 5.5 Gs for almost 3/4 of a second. So you can get really kind of tricky with this, or you can customize what you're doing, and that's just a dwell. That's as simple of a thing that you can do. It's also the most severe, but it really all comes down to physics. So the way these things work in anybody's, it's limited. The performance of these machines is limited based on how much stroke really you have available, how much space you have to move the sled from left to right. And so, like in this case, acceleration, velocity, and displacement are all related to one another, right? You can calculate, as long as you know one, as long as from the time domain perspective, if I know acceleration, I can then calculate velocity associated with that acceleration profile, and I can also calculate displacement. So, with these sleds, they have a certain standard amount of travel associated with them, or displacement, how far down the rails they can go, and our standard system is 130 inches. So, for this profile, for instance, if I'm going to target a half a G doing that UMO spec, what this says over on the right-hand side, I need not even 80 inches of total overall stroke to achieve that. So it tells you, basically our system is always calculating these things because they're always, it's all related to one another, and that's our sanity check to say, you're obviously going to get an error if you say I want to do 5 Gs using that profile, the calculator would say you don't have enough stroke or you don't have enough oomph in the system to generate that input. So it's all related. Another way to, so maybe this looks confusing, placed left to right, but if I overlay them vertically, so they're basically all on the same time scale, this gives you a better idea, okay? So if I'm gonna do this acceleration profile, this says, in this graph, at this specific time, you can say this is how fast my sled is moving as I'm going through this, because remember, anytime I'm doing positive acceleration, it's going faster and faster and faster. So it's accelerating. But then at this point, there's no acceleration. So it's going at a constant velocity. And then we actually have negative or acceleration, deceleration happening in the negative direction. So we're slowing this sled down. And then from that, we can also say, okay, where in time is the sled, right? So over that same roughly 2-second period of time, this tells you, where the sled is from a position perspective. So as long as we know how much total stroke we have available, we can get creative in generating these types of profiles, these time domain profiles. And we have, I forget what the limit is, but it's a high number of breakpoints that you can program in there into a time domain profile. And as long as you have the stroke and you have the power, the right amount of power, the system will tell you, yeah, you can do this. And it's got the performance and the stroke to simulate that unique dynamic like that, not just these slamming on the brake rings, but something like going around the roundabout. And last thing I'm going to show here is just for perspective. This is once again my braking event, right? This is reality. This is reality from a pretty aggressive sports utility, accelerating to 35, 40 miles an hour and slamming on the brakes, which to me would be much more aggressive, I would think, than what a large transport vehicle is capable of doing, full of product. So it's aggressive. This is that profile overlaid on top of it, starting at the same point, and then seeing what it looks like about 2 seconds down the road. But this is the test, right? This is the test part of it. So it gives you some perspective of what a test looks like versus what reality looks like. And I'm not, so it takes some time to soak in, all right, so how do I correlate that, right? So how do I correlate that? I'm never going to be able to simulate these 5 seconds dwell at this acceleration or deceleration level, because if I did have that capability with a sled in a laboratory, I'd need a big laboratory that runs, half a mile or whatever it might be, because it takes that long to stop, or let's just say hundreds of feet, not a half a mile, but a long distance. And so you're better off, if you want to really truly simulate reality, put the loads in the truck and go out and test it in the back parking lot or in a closed, controlled circuit. So we can't simulate that. It's just too long. So that's the static part. But the dynamic part is, is probably much more achievable. And so, if you look at the slope of this blue line, right, which is the jerk rate, well, that's got a more aggressive jerk rate than my putting on the brakes in my vehicle. And, that's something from my perspective that needs to be looked into is, what does that mean? Could these types of tests, should this have jerk rates that are more respective of, that follow reality, if we can define what reality is? This is obviously my vehicle, not a transport vehicle, but we know how to collect that data. We do as a community, and get a feel for that. And so can we start dialing in and describing and understanding these types of testing inputs better, so that we know that they're doing the right job in simulating the triggers that cause loads to shift and maybe to move, shift, collapse, because we want to be responsible about that, right? We want to understand the correlation, so that when we do this testing, we're not over. We know what, if we're deciding to over test or under test, we have an idea of relative test severity, so that we're not overdoing things. Or if we are overdoing it, we're doing it by choice. Because if we're overdoing it, that could result in things like over packaging, right? because I need to overpackage to be able to survive, or maybe a aggressive test. So questions to answer, which I don't have the answers myself, but that we're interested in helping to answer these questions. What are the appropriate test intensities? What are the right G levels? What is the right jerk rate? Jerk rates, is it a range? What are the right jerk rates, the amplitudes? What's the right amount of time to dwell? What's the right amount of time, for the jerk part of the events? What's the right amount of time to dwell at the constant acceleration? I think those kind of questions need to be answered. And then how many test events inputs, how many of those test events do we perform? And in what orientations? Is it in one direction or the other, or do we rotate? Do we do it in all four directions of a unit load? Are these types of tests standalone tests, meaning are they test failures? So we test it and we're looking to see when the load fails, and it might be multi-purpose how you can use something like this. So the standalone test, or are they added into existing transport simulation tests, so that we're focused on, instead of maybe testing the failure, catastrophic conditions, but we're testing to some kind of defined, statistically valid worst of normal, what I'll call worst of normal, something that's geared towards the more aggressive, but it's more balanced, what you might realistically expect to see in your given supply chain. And so should there be these new kind of inputs that are added to existing test standards, like in this, again, a number of the ISTA general simulation tests. So, and because remember, in let's say an ISTA 41, ASTM 4169 distribution test, we're trying to simulate a number of different dynamics that occur, or hazards that occur in a supply chain. And it's almost kind of tied to how they do occur at some level, whether it's vibration intensity and the vibration duration, but even the number of drops. If you perform drops on a unit load, or even parcel packages, you don't just drop it once from some super high drop height. You drop it a number of times in a number of different orientations, based upon what we know how they occur in the real world. Well, we probably need to do something like that here, because obviously when things are transported from point A to point B, transport vehicles start, stop, turn many times during a supply chain distribution cycle. So questions to be answered. Just one last, I'm ending now, but we are at a point where we're now have worked with the research institutes. For me, Lansmont, I've always felt like that I have questions, but I don't think we are the right people to answer those questions, since we are providers of the testing technologies. We don't want to, develop a technology and say, here, everybody needs this, go out and do these things. It's like we think that the actual application of the technology should be driven by kind of a consensus body research that takes place. So I've pushed hard over the last few years to try to get this technology into research institutes, and we've done that now in collaboration with the universities here, which are good people, good institutes, good people at all these universities here: Virginia Tech, Rochester Institute of Technology, and Michigan State University, who now all have this technology. Two of them have it installed. One is going to have it installed within the next couple of weeks, I think, very close to that, and be operational with this. And so, I'm excited, because I think we're at the cusp of really getting some tangible research results from a wide cross-section of reputable organizations to help steer us how we move forward. And with that, I'm going to kind of try to stop talking. I'm basically at the end, but I just did want to mention another short course. So, part of my role also is in working with the universities, is to also cooperate with them, kind of represent Lansmont in research activities that they take place, not just from giving the helping get access to technology, but actually, if I can, help participate in research as a member of that effort. And so we've done a short course together with Dr. Laszlo Horvath at Virginia Tech University, and we just set a date for a course that we're going to do in the fall for Advanced Packaging Dynamics, Measurement and Simulations, September 10th to the 12th. in the fall at Virginia Tech, and part of that research will be focused on using, it's not only associated with this technology. They have, just like the other labs, all kinds of, from the Landsmart, I guess, or testing perspective, all kinds of dynamic testing equipment. But part of it's going to be focused on the addition of this this sled now at Virginia Tech, the acceleration sled. And so, get some hands-on experience with that, which will be pretty cool. Give you an idea of what this looks like. These little events, not super exciting, depending on what the real world numbers are. 23 Gs, that was 0.5 Gs. And that's looking at something like, what a roundabout, that back and forth oscillatory motion looks like. So, I'm done. Thank you for your patience, sticking with me. I know I've run over my hour. I like to talk. I apologize for that. And I'm going to now move, ask Sharon to come back, and Laszlo, if you're there. Laszlo's with us. He didn't present anything, but he's with us. If anybody has questions for myself and or Laszlo, happy to answer them now, and obviously happy to answer things by email if anybody has any questions. Thanks for your patience and participation.
Thanks so much, Eric. If anybody has any questions, now would be the time to type it into the question box. We've gone a little bit over time, so even if we don't get to answer it here today, we will be answering it on one of the on-demands that we sent. But there is still time, so please put your questions in the question box and let's hear what you've got to say.
Yeah, and once again, apologies for running a little bit over, but it's hard to scrunch down some of this stuff into. It's always a challenge for me to scrunch it down, especially because I like to talk and I get excited about simple things like load stability or this type of dynamic. It's really better served in something like a short course, probably a half-day course to cover it all in detail. So apologies. And anybody that is still on the line, feel free to email me or Laszlo directly if you have questions about any of the
Eric,
content.
sorry, there is one question, and I don't know if it will be a very difficult question to answer, hopefully not, but the gentleman is asking, can you ballpark the price of a true motion sled?
Yeah, I don't want to, I guess I would ask the whoever that is to email me, because I don't want to, I feel personally that I don't want to do that here. Because I'm not trying to sell it. I mean, obviously we want, like anybody wants to sell things, but I would rather not use this platform and start pricing it out. But I'm happy to answer that directly with whoever asked the question.
Thanks, Eric. I can also pass his details on to you, so then you can reach out to him.
Yeah, I'm not trying to hide anything. It's not trying to make it a sales pitch either.
No problem. There's another question. Are there any extensive legal fees for not adhering to FMCSA performance criteria?
I don't know. I hate to say, I don't know. I'm not, in that those requirements have been there. I think if you look at some of the documentation, I mean, the most, I'd say the last update was 2012, something like that. I never hear any mention of it with anybody that I work with, either from the carrier side or shipper's side. And so basically, like even with the UMOS or the EU requirements, it's one of these, you have to prove capability. So if an inspector from the police or whatever, on the highway pulls you over, and they, see your, like in the US, they say, let's see your license, your registration. I don't know what other kind of things that a truck driver might have to have, but they might say, what are you carrying? And if there's not been an incident with the load, they might not ask to see your, the UMOS certification, or says you've been tested and met the requirements. You've got that documented. But if there's an accident, your truck tips over, because the load shifted, all the load shifted as you're going around the roundabout and it tipped over, or something falls out the side, they're going to come and say, can I see your testing certificate, all these things, plus the testing certification. At that point, they're going to, you've got some liability on your hands. So I don't think, it's really there it's there to, what we would say, CYA, cover your rear end. And certainly if an incident occurs, but you just have to, you are liable for it. I just don't know how much that comes up as an issue, or how much they really regulate that here in the US. I know in Europe it's a much more stringent issue. People take it a lot more seriously.
Thanks, Eric. I don't see any further questions, so I think we'll draw the webinar to a close for today. As Eric said, you've got his details, and also if you reply to the invite that you received for the webinar, that will also come through to us. So there's various ways for you to contact us if you have any further questions. Thanks very much, Eric.
Yeah,
thanks for being with us, Laszlo.
Sorry, Sharon, but I just want to remind once again that when we post the on-demand, before we post it, I will make sure that all my videos are on there and playing in good quality.
Awesome. Thank you very much, Eric. Thank you, Laszlo. Thank you, everybody, for joining us. And we will be releasing new dates for upcoming webinars soon, so please keep an eye out for those and enjoy the rest of your day.
Thanks, Sharon. Thanks, Laszlo. Thank you, everybody who are still there. Take care.
Thanks so much, guys.